Hello, I'm Professor von Schmohawk, and welcome to YU. In the last several lectures, we introduced several forms of linear equations whose graphs are lines in the xy plane. In this chapter, we will use linear equations to solve some real-world problems.
Why, hello, Hulk. I'm so happy to see that you are gainfully employed this summer. I was looking for someone to drain my pool tomorrow.
Sure, Professor Athaline, but I'm supposed to clean Mr. Squeegiopolis' pool tomorrow.
Well, I'm sorry, Hulk, but I need it drained by 8 p.m. tomorrow. I'm having some very important guests over, and the pool must be completely empty by the time they arrive.
Okay, Professor, I'll figure something out.
Oh, Hulk, you're such a resourceful young man. I knew I could count on you.
What's the matter, Hulk? Have you perhaps encountered a small resource scheduling problem?
Okay, Geekman, how much is this gonna cost me?
Well, my normal short notice subcontracting fee is $50 an hour, but I'm running a special today. Only 49 buckaroonies an hour.
Yeah, well, I'm running a special today on knuckle sandwiches.
Perhaps I didn't mention that you're eligible for the double extra special very best buddy rate of $3 an hour?
Well, just make sure you have that pool empty by 8 p.m. tomorrow.
Yes, sir, Mr. Mooshbasher. Rats, it's almost noon. I'd better get cracking. Start pool draining at 12 noon. It's 1:30 and the water level is 10 feet. Hmm, 3 o'clock and the water level is 8 feet. Yikes, this pool better be empty by 8 p.m.
Well, it looks like ace algebra student A.V. Geekman may be in hot water. Will the pool be empty by 8 p.m.? If we graph the water depth versus time, we might be able to figure out how long it will take for the pool to completely drain. We will plot the amount of time since the drain was first opened at noon on the horizontal axis and water depth on the vertical axis. We know that at 1:30, 1.5 hours after the drain was opened, the water level was 10 feet. And at 3 o'clock, after 3 hours of draining, the water level was 8 feet. However, there is one problem. With only 2 data points, it is impossible to determine whether the water level is dropping by the same amount every hour, or if the water level drops more quickly as time goes on, or perhaps if the water level drops more slowly with increasing time. Taking one additional measurement a third time would allow us to determine which scenario more accurately represents the water level as a function of time.
Dang, it's 6 o'clock already. And we still have 4 feet to go.
We can now add a third data point to our graph of water depth versus elapsed time, since AV has determined that after 6 hours, the water depth is 4 feet. It looks like these 3 points all fall on a line, so maybe the function we are graphing is linear. We can verify this mathematically by calculating the slopes of the line segments connecting the first and second points, and the second and third points. If the slopes of both segments are the same, then all 3 points must lie on the same line. As we saw in the chapter on slope, we can calculate the slope of a line which passes through 2 points as the difference in the point's y-coordinates, delta y, divided by the difference in their x-coordinates, delta x. Dividing delta y by delta x, we get -4 over 3, or a slope of -4/3. Now let's calculate the slope of the other line segment. Once again, we take the difference in the y-coordinates, delta y, and the difference in the x-coordinates, delta x. Dividing delta y by delta x, we get -2 over 3/2. We can simplify this complex fraction by dividing -2 by 3/2. This is the same as multiplying -2 times the reciprocal of 3/2, or 2/3. -2 times 2/3 is -4/3. So the slope of this line segment is also -4/3. Since the slopes of these two connected line segments are the same, all 3 points must lie on the same line. We can therefore assume that the water in the pool is draining at a constant rate and that the water depth as a function of time is linear. Since we know this line's slope and at least one point which falls on the line, we can write the equation for this line using the point-slope form. If we choose the bottom point, which has coordinates 6, 4, to use as the known point in the point-slope formula, then x1 is 6, y1 is 4, and the slope m is -4/3. Now that we have an equation which represents water level y as a function of elapsed time x, we can plug in different values for x to see what the water level will be at those points in time. For example, an elapsed time x of 0 corresponds to the time when the drain was first opened. If we set x to 0, then the resulting value of y will tell us the initial depth of the pool. Completing the arithmetic, 0 minus 6 is -6, and -4/3 times -6 is +24/3, or 8. Adding 4 to both sides of the equation allows us to cancel -4 on the left, leaving us with y equals 8 plus 4, or 12. So the initial depth of the pool when the elapsed time x was 0 was 12 feet. If we would like to find out how long it will take for the pool to be empty, we can set the water level y to 0 and solve the equation for x to see what the elapsed time is at that point. We start by setting the value of y to 0, and we can then write 0 minus 4 as -4. Since we are trying to find the value of x, we want to rearrange the equation so that x is alone on one side. To do this, we must first eliminate the -4/3 by multiplying both sides of the equation by the reciprocal of -4/3, which is -3/4. Since anything multiplied by its reciprocal is 1, we can replace -3/4 times -4/3 with 1. Now, since everything in the parentheses is multiplied by 1, we can eliminate the 1 and the parentheses. Completing the arithmetic on the left side, -3/4 times -4 is 12/4, or 3, and adding 6 to both sides allows us to cancel the -6 on the right, leaving us with the equation 3 plus 6 equals x. Adding 3 and 6, we have 9 equals x, or equivalently, x equals 9. So when y is 0, x is 9. Since x is the elapsed time, and y is the water level, this result tells us that when the water level y is 0, the elapsed time x will be 9 hours. Since the drain was opened at noon, the pool will not be empty until 9 o'clock.
Excuse me, Professor von Schmohawk. Did I just hear you say that my pool will not be empty until 9 o'clock?
Yes, Professor Etheline. According to our calculations, that is correct.
But I distinctly remember telling Mr. Moose Masher that my pool must absolutely be empty by the time my guests arrive at 8.
Excuse me, if I may interject here for a moment. I believe that it is possible to calculate the exact depth of water in your pool at the time your guests will arrive. If we start with the equation for water depth versus elapsed time, and set the elapsed time x to 8 hours, we can then solve this equation for y, which represents the water depth, and thereby determine the depth at exactly 8 o'clock post-meridian. As we all know, 8 minus 6 is 2, and negative 4/3 times 2 is negative 8/3. Then, adding 4 to both sides, the 4's on the left side cancel. We can then write 4 as 12/3, and negative 8/3 plus 12/3 is 4/3. So, according to my calculations, the water depth at 8 o'clock p.m. will be exactly 4/3 feet. In other words, 1 1/3 feet. Now, since there are 12 inches in a foot, 1/3 of a foot is 12 inches divided by 3, or 4 inches. So, 1 1/3 feet is 1 foot 4 inches. We can therefore deduce that when your guests arrive, your pool will contain exactly 1 foot 4 inches of water. Nope. Professor Etheline, how much longer do I have to entertain your guests?
Why, you're doing a splendid job, AV. I'll let you know when it's 9 o'clock.
Yeesh.
Thank you, AV. It's exactly 9 o'clock, and just as calculated, the pool is empty. Yeehaw!
We have seen how linear equations can be applied to real-world applications. In the next lecture, we will see how real-world quantities can be calculated using formulas, also referred to as literal equations, which relate two or more quantities.